Hello everyone. I, Sneha Sau, along with my teammates Arpita Samantrai and Mehak Fatima, are going to present on the topic intelligent structures and materials. As we know, concrete is the second most used resource in the world, and most of the infrastructures around the world are built with concrete. However, due to degeneration of concrete materials, complex interaction between concrete materials and the service environment, absence of advanced design and condition assessment tools, and timely maintenance, many concrete structures are in utter despair. That is why significant efforts are made to render the failing infrastructures back to a serviceable and safe state. Smart concrete is a promising engineering material for addressing this issue by improving serviceability, safety, reliability, and durability of the infrastructures. Therefore, smart concrete and structures provide new approach for maintaining sustainable development in concrete materials and structures. Now, what are smart materials and structures? Smart materials, also known as intelligent materials or responsive materials, are created materials with one or more properties that can be significantly altered in a controlled manner by external stimuli such as stress, moisture, electric or magnetic fields, light, temperature, pH, or chemical compounds. Now, some features that make them distinguished from other materials are transiency, immediacy, self-actuation, selectivity, and directness. Transiency is the response to different stimuli and situations in various states. Immediacy is the response to the external effects without wasting time. Self-actuation or intelligence is the ability that is present inside the matter. Selectivity is the response to distinguish and predictable. Directness, both act and react are occurred in the same place. A smart material or intelligent structure is essentially a structure with built-in smarts. This is achieved by integrating several key components, and that are first is the smart materials. The substance undergo a real observable change in order for it to be considered smart. For example, shape memory alloys are used, which can return to a predefined shape after deformation, potentially repairing minor cracks. Sometimes piezoelectric materials are used to generate electricity when stressed, enabling self-powered sensors. And self-healing concrete is also used, which contains capsules that release healing agents to mend cracks. Now, sensor networks. These are embedded throughout the structures to monitor its health and performance. Control system. These are used to analyze sensor data and trigger actions such as activating dampers to counter vibrations during an earthquake. So the smart materials are divided into two main categories: passive smart materials and active smart materials. Passive smart materials are able to transfer some types of energy, whereas the active smart materials are divided into two types. First ones alter their characteristics on exposure to external effect. The others can change energy from one form, that is thermal, chemical, nuclear, mechanical, to another form. Intelligent systems are designed to possess sensing, actuation, and control capabilities, allowing them to adapt, respond, and even self regulate in self time to changing environment conditions, loads, and usage patterns. So, the design principle of smart concrete and structure are greatly different from conventional concrete and structures. The appropriate materials, which possess the ability of sensing, actuating, and controlling, will be selected after the goals are ascertained. Finally, the system characteristics will be optimized and examined. The design will be finished if the system characteristics satisfy the goals. If not, redesigning will start from the material selection until the goals are achieved. Now, why do we need such kind of structures? These structures built with intelligent materials can sense external loads, assess the internal stresses and damage caused by the loads, and respond appropriately if necessary. The most probable candidates for the initial application of these materials are high performance structures such as skyscrapers, including intelligent buildings, bridges, and those facilities where failure presents large safety concerns, such as nuclear waste containment vessels, bridge decks and dams, and structures under construction. So, integrating these intelligent structures and material often offers significant advantages. So, the advantages can be enhanced structural resilience, improve safety, reduce maintenance costs, increase sustainability, lifespan extension. Overall, intelligent structures and materials represent a major leap forward in civil engineering. Now, now we will discuss the past research works that has been done in this field in the past few decades. The field covers a wide range of topics, including smart material, sensors, actuators, control system, and structural health monitoring. Integration of interdisciplinary knowledge from fields like material science, mechanics, control theory, and computer science drives innovation in intelligent structures. Challenges and opportunities exist in utilizing smart materials for enhancing performance, efficiency, and functionality in aerospace, automotive, biomedical, and civil engineering application. A comprehensive understanding of the state of art is provided through reviews, which discuss historical context, recent advancement, technological innovations, and potential future directions in the field. So in Japan, from July 1987 to November 1989, the Council of Aeronautics, Electronics, and Other Advanced Technologies of Science and Technology Agency supported a discussion on intelligent materials, and an attempt was made to study this new concept from the perspective of professionals representing a broad range of disciplines. The concept of smart concrete and structures was first proposed by Japanese researchers in the late 1980s. Since then, Yanagda of the University of Tokyo developed self-test concrete by involving glass and carbon fibers into the concrete in 1992. So now I would like to call Arpita to continue with the rest.
Thank you, Sneha. Now, I would like to discuss the objectives of intelligent structures and materials. Designing and implementation of intelligent structures and materials involves a multidisciplinary approach, integrating principles from material science, engineering, and computer science. Material properties include possession of specific properties tailored to the intended application, such as shape memory alloys or piezoelectronic materials, can be particularly useful for adaptive structures. Structures must maintain its stability, strength, and functionality under various loads and environmental conditions. Now, cost effectiveness also plays an important role. It is important to balance performance with cost such that the efficiency and lifespan is extended and maintenance requirements are reduced. Sustainable materials and manufacturing processes should be prioritized to minimize environmental impact, such as using recyclable or biodegradable materials, reducing energy consumption during production, and considering end of life disposal. Adaptability to environment conditions. Intelligent structures should be able to adapt to changing environment conditions such as temperature fluctuations, moisture levels, and external loads. Embedding sensors and actuators into the structure enables real time monitoring and control, facilitating adaptive responses to changes in the environment or operational conditions. Intelligent structures often rely on sophisticated algorithms to process sensor data and make informed decisions. This involves developing algorithms for data fusion, pattern recognition, and predictive modeling to optimize performance and efficiency. Consideration should also be given to how the structure will interact with its users and occupants. User-friendly interfaces and ergonomic designs enhance usability and user satisfaction. We need to address these goals and parameters and to create intelligent structures and materials that are not only functional and efficient, but also sustainable, resilient, and adaptable to the needs of both humans and the environment. Here we can see the biometric design of smart concretes and the design process of smart concretes and structures, which start from application conditions and goals to the final formation of smart concrete and structures. Now let's discuss the categorization of smart materials. There are various types of smart materials, one of which is shape memory alloys. These are the materials that can return to a predetermined shape when heated and are useful in self-healing structures. Piezoelectric materials generate electric charge when mechanically stressed, used in sensors, actuators, and energy harvesting devices. Magno Magnetostrictive materials change shape in response to a magnetic field applied in sensors, actuators, and to detect structural deformations. Electrostrictive materials alter shape when an electric field is applied. It is utilized in microactuators and in active vibration control in structures. Chromic materials change color in response to external stimuli, and pH sensitive materials change properties like color or conductivity based on pH levels. They are crucial in monitoring corrosion in structures and in water treatment systems. Electrorheological fluids are the fluids whose viscosity can be controlled by a magnetic or electric field, used for adaptive damping systems, seismic dampers, and vibration control in infrastructure such as bridges and buildings. The classification of smart structures and concrete include self-sensing concrete that are able to sense concrete conditions and environmental parameters such as stress, strain, crack, temperature, and humidity. These are also called self-monitoring or self-diagnosing concrete. Self-healing is the ability of concrete to repair its cracks autogenously or autonomously. Self-healing of cracks in concrete contributes to a longer survival life and makes the material not only more durable but also more sustainable. Self-adjusting is the ability to respond to loading or environment conditions for the remaining capacity of concrete. Self-heating refers to concrete material used in electrical resistance heating based on Joule effect, also called electrothermal concrete. It has excellent potential for de-icing and snow melting of parking garages, sidewalks, driveways, highway bridges, and airport runways. Self-cleaning property of concrete means the ability of effectively resisting wetting by water and aqueous solutions or diminishing air pollution and pollution on the concrete surface. Electromagnetic shielding or absorbing concrete can reflect or absorb EM radiation, which thereby acts as a shield against the penetration of the radiation through it. These are done by introducing conductive fillings and ferromagnetic materials. Energy harvesting concrete refers to concrete harnessing energy from various ambient energy sources. Light transmitting concrete use optical fibers in the concrete that act like slits and carry the light across throughout the concrete. Now we come to sensing and actuation. These terms have been used multiple times in this presentation. What it actually means is that intelligent structures and materials can be equipped with sensors and actuators that enable real-time monitoring and response to external stimuli, enhancing their functionality, performance, and resilience. Strain gauges, fiber optic sensors, piezoelectronic transducers, smart materials, and wireless sensor networks are some of the few sensors and actuators used to perform this operation. Now, I would like to call my friend Mehak to talk about control of smart structures.
Hello everyone. I'll continue with the control of smart structures. Control systems play a crucial role in managing and optimizing the behavior of intelligent structures and materials by providing real time monitoring, feedback, and adjustment mechanisms. Here's how control systems contribute to this process. Real time monitoring. Control systems continuously monitor various parameters such as structural stress, temperature, humidity, and environmental conditions using sensors embedded within the structures. This data is collected and analyzed to assess the current state of the structure and detect any deviations from desired performance criteria. Next is feedback control. Based on the data collected from sensors, control systems can implement feedback mechanisms to regulate the behavior of intelligent structures and materials. Then we have the adaptive control, in which the control systems can adaptively adjust to the behavior of intelligent structures and materials in response to the changing stimuli. This flexibility allows structures to dynamically optimize the performance over time, considering the factors such as varying loads, environmental changes, and user preferences. Next is optimization algorithms, in which they utilize optimization algorithms to analyze sensor data and determine the most efficient strategies. Integration with actuators. The control systems often interface with actuators embedded within intelligent structures to implement corrective actions or adjustments in real time. Remote monitoring and control. In some cases, control systems allow for remote monitoring and control of intelligent structures that enable engineers to operate or monitor the performance, diagnose issues, and implement adjustments from a centralized location. Overall, the control systems serve as the brain of the intelligent structures and materials, enabling them to dynamically adapt, optimize, and respond in real time. Now we have the implementations of the smart and faculty of civil engineering building. This building features self-healing concrete developed by researchers at the university. Microcapsules containing bacteria and nutrients are embedded in the concrete mix, which are activated when cracks form, allowing the bacteria to produce limestone, effectively repairing the cracks. The energy generating smart bridge in Netherlands. This bridge incorporates piezoelectric elements within the concrete structure. They harness the kinetic energy to generated by the pedestrians and vehicles across the bridge, converting it into electricity to power nearby streetlights and other infrastructures. The Salerno Maritime Terminal in Italy features a sculptural roof made from fiber reinforced concrete, which incorporates fibers such as glass, steel, or synthetic materials to enhance the concrete's properties. Next examples, we have the Parkview Green Fang Chao Di in Beijing, the Drunk White Lotus School in Ladakh, the University of California, San Diego, the Hastia Community Center in Norway. Next on, we come to the challenges faced in the development and application of such smart structures and materials. The major challenge to building and using a comprehensive sensor system is that a variety of physical parameters must be measured. Sensing and data processing are complicated because most of the measurements exhibit dynamic behaviors with time scales, and also modem data acquisition hardware can collect enormous amounts of data, yet only a small fraction may be useful. Although smart concretes and structures feature high performance price ratio, low life cycle cost, and low life cycle cost, their relative high production cost primarily limit the large scale production, and therefore some low cost but effective functional component elements should be chosen to constitute smart concretes and structures. Because concrete is fairly complicated material, the related effect of its own components on the reinforcing capacity of functional fillers is very complex. In addition, the specific smart concrete and structure only possess a certain intelligent behavior, which is not satisfying enough. Now, we come to the future prospects of the smart concretes and structures. The development of multifunctional, multidirectional, and compound smart concretes and structures will be the main driving force in this area in the future. In future works, much effort should be invested in developing more comprehensive and precise works, forecasting the smart behaviors of smart concretes and structures based on the experiments and numerical stimulations. Some novel retrofits of smart concretes and structures should be developed based on other disciplines such as AI, biomimetrics, electronics, and aerospace. It is suggested that subsequent studies on application of smart concretes and structures should be aimed at establishing a uniform method, guidance, and specifications. At the present stage, the properties of each kind of the aforementioned smart concretes and structures have not yet reached a stable, repeatable, and optimized state. It deserves extensive further investigation to achieve the same. Now we come to the conclusion. To conclude, the ultimate extent to which structures are built with intelligent materials depend on the technology having positive economic, engineering, safety, and cost benefits. Early applications could include large structures such as skyscrapers, intelligent buildings, which would incorporate fiber optic sensing systems into the conventional fiber optic communications network. An intelligent building system would control internal and external telecommunications, security systems, heating, ventilation, etc. At the same time, it would also measure the wind and, in some cases, earthquake loads on the building, delegating the appropriate responses, such as activating active anti-vibration systems. The intersection and integration of these approaches promise great benefits, especially for the purposeful design and programming of new behaviors of spatial structures. Buildings and spaces equipped with such active programs will be more responsive and adaptive to new functions and uses, and more resilient to volatile changes of environmental and social conditions. Once structural measurement are deemed worthwhile, such a sensing system could be installed for a relatively low additional cost. The immense opportunities arising from the innovative application of smart materials need to be boldly explored in the field of design and construction. Following are the references we used for the in the process of development of our presentation. With that, we have come to an end. Thank you.